Today we'll look at something called stats models. All right, so stats models. So Python, like the base Python, hardly has anything that is useful for statisticians to do, like statistical modeling. Okay, now Python is super popular for data science, data analysis, and stuff. But all of these things, you got to like load up libraries and packages and different things, okay? And so there's a few libraries that are quite popular, and I would say the most popular one for like analyzing data, the machine learning thing, is scikit-learn. Okay, so we'll cover that next. Okay, and you can just type in sklearn, and that will take you to this the scikit-learn.org, and this is machine learning in Python. And I would say this is like super powerful stuff. Did everyone take 102B with me? Who did not take 102B with me? Okay, a handful of you. All right. So, all of this stuff that we've covered in 102B, at least in my class, this makes an appearance in scikit-learn. Okay. And then the other thing that's big is stats models. Okay. So stats models is more of like traditional statistical analysis. Okay. So if you want to fit like a linear model and do your traditional analysis where you get the coefficients and you get test statistics on each coefficient and a p-value for each coefficient, and you check all of these residuals and you do ANOVA. Stats models, I would say, is my recommendation. All right. You want to do more complex stuff like machine learning stuff, then you'd use scikit-learn. All right. So a big difference between R and Python is like in R, technically with Python anyone can make a package, but in R you have like 1,000 bajillion packages out there, right? And they're in varying quality. Some are really good, some are not so good. Okay. You also have the base tools built in, like LM is built into R, and LM is like so great. Okay. And I think that's why R remains popular among statisticians. Okay, even though Python is gaining a lot of popularity, especially for machine learning, as far as just like doing basic statistics, it's hard to beat R's LM and ANOVA features. Okay, but anyway, we'll talk stats models first. This is for your classical statistics, all right? And then scikit-learn is better for machine learning stuff, okay? Technically, you can still run linear regression and all sorts of like logistic regression, these traditional methods in scikit-learn, okay? But you're gonna get a little bit less, it's less statistician friendly, okay? So anyway, we are going to start off by importing all of your usual libraries. NumPy as NP, pandas as PD, matplotlib.pyplot as PLT, Seaborn as SNS. So this thing just keeps growing, right? All right, and then so today we are bringing in stats models as SM and stats models formula as SMF, okay? Statsmodels.api, statsmodelsformula.api as SMF, okay? And so we'll import all of those things. Always that takes a few seconds to get all of the libraries loaded up. All right. And we will do just kind of like your minimal ordinary least squares example here, okay? So I'm going to set X is this array 1, 2, 3, 4, Y is another array 2, 6, 4, 8. I can plot this, and this is what our plot looks like, okay? So dot, 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 okay? 4 dots. Positive correlation to the right, positive correlation. We're going to fit a linear model, okay? I'm assuming everybody remembers all of their stuff from 101A, right? All right, we can make a data frame out of this. So I've got my two arrays, and so I make a data frame using this dictionary. I'm going to say x is x and y is y, and now I have a data frame. 4 observations, 1, 2, 3, 4, and I'm going to call that data frame D. And if you wanted to do just seaborn, okay, this is your linear model plot. All right, and so this is the line. Seaborn, again, is just for visual exploration. There's no way for from seaborn, you can't get back your slope and intercept. Right? You just have to look at it and go, all right, I guess that's reasonable. Okay. All right. So in stats models, SMF, the formula API is similar to R's formula API. Those are some differences, of course, but this is very much like the LM function in R. So we're going to say the model, we're going to assign smf.ols, the output of that, to model, okay? So SMF is for stats models formula API. And we're going to say we want ordinary least squares, OLS, and we're going to do y as explained by x. Y tilde x, the data is D, right? So this already feels familiar, right? Okay, so I run that, and it's been assigned, and we can ask, all right, print out the model. Okay, and this is what it says. It says stats model.regression linear model OLS object. Okay, so this is one thing that is very different about Python, is that this command only initializes a model. All right, so it says, all right, we're going to make this model, but it doesn't actually attempt to fit the data. All right, so if you want to fit the data, all right, if you want to fit the data as in give me the coefficient estimates, all right, you have to call the .fit method. So you do model.fit, all right? And this is, for whatever reason, this is how Python has decided to do things, okay? At least the authors of stats models. So you call, we're going to do model.fit, and we're going to assign that to results. All right, now we can ask, all right, what are these results? All right, and so so what we will do is we will do results.summary. Okay, I don't know what all of this, I'm not sure what all of this commentary on boys and girls is. All right, so results.summary prints this out. It says the intercept is 1, the slope, the coefficient for x is 1.6. So our slope is 1.6. We get a standard error. We get a test statistic t. We get a p-value for that thing, right? The intercept is 0.7. My p-value for the slope is 0.2, right? So at least with 4 data points, we don't have evidence that the regression, that there's even positive correlation, okay? Evidence of positive correlation, saying, you know, we could get something like that by random chance 20% of the time. Okay, and then it also prints out all of these other things, right? So it says your dependent variable is y, your method, your model. You ran this at 5:16 p.m. You have 4 observations, 2 degrees of freedom for the residuals, 1 degree of freedom for the model. Your R-squared is 0.64, and all of these other things. AIC, BIC, F statistic, log likelihood, all sorts of stuff, right? Okay, and that's it. You want to make it more complicated, you can do that, right? You can, if you want to fit the thing, you can call stats models graphics, and there's something called an AB line plot, and you can say the results are the results that we have stored here, okay, which is this output, results.summary. All right, and you add the plot, all right, and all it does is it just graphs this line. Okay, so it's just a bunch of new commands. So as far as specifying your model, this is what you have, all right? And just like everything else just like everything else, go to the documentation. You can look at the examples for linear regression models, and you can hit the examples for ordinary least squares regression. So here, this example, they've got x and then x squared, okay, just some random values, and this is the traditional fit the non-formula API, okay, which I'll show you that in a moment here. Okay. Always look up the documentation. Okay. So again, you don't have to worry about this for the midterm, but I imagine some of you might use this in your project. Some of you might do traditional methods, others of you will do machine learning stuff, okay? So, so here you can ask for ANOVA. You get your ANOVA table, which has the degrees of freedom, the sum of squares, your mean squares, your F ratio, okay? And then you can also ask it to make predictions. If x is 2, what do I predict? It's going to predict 4.2. So you've got results.predict and things like that. Okay. The other method for stats models is to use NumPy array notation. Okay, and this is pretty much how everything in scikit-learn operates. So scikit-learn uses the array notation, and so so basically this is this, okay? And so stats models has a similar setup so that you can use array notation and do it, okay? So basically stats models has the formula notation for people transitioning to Python from R, okay? So this should look familiar as a user of R, okay, the y tilde x. And then stats model also has the NumPy array notation for people who are trying stats models out after they've become comfortable with scikit-learn, okay? So it's got both setups, okay? And so here is x. X is just this NumPy array, 1, 2, 3, 4. And what we can do is we can make a matrix out of this by calling stats models add constant, right? So we're going to add an intercept term. And if I print out x, now I get this, okay? So it's turned everything into floats, and we've got a column of ones and the column for x, 1, 2, 3, 4, right? And this is basically array notation so that you can have, your model is that, y hat is equal to beta times x, right? So we're all okay with the linear model expressed in matrix note form, right? Okay, so this is what we have, and so if you want to do stats models OLS, okay, you call sm.ols. Now notice that over here we have SMF, stats models formula, little OLS, and then when you do a NumPy array notation, it uses capital OLS. I don't know, okay? Again, when you specify this only specifies the model, doesn't actually do anything. So you specify the model, and then you do model.fit. Model.fit then estimates the parameters, and then we ask for the results, okay? And so these results look pretty much exactly the same as these results, right? So output's pretty much the same thing, except the way you called it is different. You have to give it your vector of output values, which is y, and then your vector of input values, which is x, okay? And for the x matrix, we had to add a column for the constant, okay? Because it's basically estimating these things for OLS in matrix form. So if you want to estimate the constant, you have to add the column for the constant here, okay? And so OLS is specified like this, y comma x. And then so you define the model, you initialize it, then you do model.fit, and then you print out the results. Okay. If you wanted to, you could do like linear algebra. All right, this is silly, but you could do like x transpose x inverse x transpose y using the infix matrix multiplication operator, right? This is a new thing. This matrix multiplication operator is like a new thing for NumPy. I think it's only been around for a few generations of NumPy. It hasn't been around since the beginning. So you might see other things called like np.dot for the dot product instead of the infix matrix multiplication. So anyway, you could do this and you'll get your slope and intercept. But you won't get any of the other stuff. So anyway, stats models, all of this stuff, right? And again, this is just an introduction. And then I just refer you, okay, depending on what you're going to do, whether it's fit a linear model or do something more complicated, so you can just type in OLS here. And look for any of these things, right? So stats models dot formula dot API. Okay, you can look up any of these things and ask for examples of how this stuff is specified. So here's the formula. This probably, I think, looks familiar, right? You have the output, tilde, and then all of the inputs with plus signs in between. And then you ask kind of the results. You do ols.fit, so on and so forth. Okay, so just spend time reading the documentation if you plan on using stats models. All right, so that's just a super quick, short intro to stats models. These are just other examples. Read through the examples. They're also quite useful. And so you can see, so here is, x. They've made the matrix x squared. They add a constant to it, okay? And then as far as the y values go, they did x times beta. So this is a linear model plus some errors. Right. So now this is the simulated data, and here we're going to fit a model. We're going to do OLS y comma x. So this is the NumPy matrix notation model.fit. Print out the summary, okay? And so here we get the coefficient estimates. Here's the estimate for the constant, for the x1 term and the x2 term, which is x squared, okay? And you get all of these things, right? So you can kind of scroll through, read through these examples. Okay, we'll end that right there. And then now I'm going to introduce just the very basics of scikit-learn. Okay, let me go ahead and close that one. Here, let me clear all of this out. Okay, so scikit-learn has a whole bunch of machine learning models built into it. And there are tons, okay? You can come to scikit-learn and you have classification models, regression models, clustering, dimension reduction, and then a bunch of stuff for model selection and pre-processing, okay? So model selection includes tools for things like cross-validation, and it also has something called grid search, which is really handy, all right? There's other things for pre-processing, which includes things like feature extraction. So if you want to take your x and you want to make like x squared and x cubed and stuff like that, you've got pre-processing things. But here we'll just start off with like the most basic stuff, okay? So I'm going to just click regression, okay? And this takes me to supervised learning, and it lists off a whole bunch of these things. All right, so we've got ordinary least squares for regression, okay? Then you've got ridge regression, lasso, multitask lasso, elastic net. I don't know what multitask elastic net is. Okay, least angle regression. I don't know, a whole bunch of stuff. Lars lasso. I don't even know what these things are. Generally, what happens is somebody publishes a paper and says, I've developed this new statistical method and it's useful in these niche applications and situations and stuff like that. And then, and someone will go, oh, this is great. And then they'll write some code, suggest it to be added to scikit-learn. It gets a little bit of community review, and then they'll add it. So they're constantly adding new machine learning stuff. So every time I check, there's always something new here, and I'm like, oh, I have no idea what this is, right? But you know, so a lot of these things, like the OLS, ridge regression, lasso, like, okay, we get those, right? Elastic net is kind of the hybrid of those things. Like we know how to do those, right? And then you have a whole bunch of other stuff, right? So you've got linear and quadratic discriminant analysis, support vector machines, gradient descent, nearest neighbors, Gaussian, you know, all sorts of stuff. Naive Bayes. Oh, look at all this stuff you guys learned in 102B. Okay. So anyway, all of this stuff is listed there, and the nice thing about scikit-learn, I guess the dangerous thing also, okay, is that you run pretty much all of these models in the same way. You specify the model, then you call model.fit, and then you print out the results. Model.predict to make predictions, things like that. It's kind of just like once you learn how to drive one car, you can be thrown into like a whole bunch of different cars and drive it. But then, you know, they give you a whole bunch of stuff, and maybe you're like, well, I'm going to just try this thing. I've never tried that. That sounds neat. Maybe you shouldn't. Maybe it doesn't make sense to apply that method in this context, okay? But of course, you need to have statistical training and at least some understanding of the model itself to know whether it makes sense to apply this method. Maybe the danger of scikit-learn is that it makes all of these things very accessible as far as like just running the code. Running the code is super easy, but maybe the interpretation's a little bit harder, okay? I hope you guys, you know, you're gonna graduate with your degree in statistics here, and I hope you'll at least say like, oh, it makes sense to use this model, and it doesn't make sense to use this model in this situation, right? That we're not gonna just blindly say, oh, here's something fancy and new, let's just try it, right? We'll do some thinking about our data. All right, so anyway, import the usual stuff, and then, so I would not say, don't just do import sklearn as sk something something, okay? Because sklearn is huge. It's got so many things. So from each of these things, like if you're only going to just do a linear model thing, okay, only import what you need. So here this says, you know, from sklearn import linear model. So we're only going to just import one of the little modules that's available in sklearn, the linear model module, okay? All right, so here I'm just generating some random data, okay? So I'm going to just do x is 10 plus some random noise, okay? So we're going to get values between like 8 and 12. And then y is going to be 1 plus 0.8x plus a bunch of random noise as well, okay? And so this is what I get. I'm sorry, not random, this is not random number, this is random digits multiplied by 10. So you get values from 0 to 10, we add the line to add some random noise, this is what we get. Okay, if we ask what's the shape of y, it's just a vector, okay? It's a one-dimensional array. And now what I'm going to do is I'm going to initialize the model, Okay, I'm going to do linear.model, linear regression, fit intercepts true. Okay, so we're going to go ahead and do this. All right, so this just defines the model. If I print out the model, it just says I've initialized this thing. It's going to fit and intercept. It's got a bunch of other options, but this just defines the thing. Oh, sorry. Right now we haven't even estimated the coefficients. Here is x. X is just again one-dimensional vector or a one-dimensional array like this, and that's why we need to fit the intercept. Okay. For scikit-learn to work, you cannot feed, y has to be a one-dimensional thing, but x has to be a matrix. So I'm just going to reshape this to be 50 by 1. Okay? So all I did was I took x and I reshaped it to be a 50 by 1 matrix. Okay? Scikit-learn requires that x be a matrix. All right, so now, because I told scikit-learn fit intercepts true, I don't have to do that business of adding the constant column to x, okay? So I can just do model.fit x comma y, all right? And pretty much all of scikit-learn runs off of this format, model.fit x comma y, right? Whether it's ordinary least squares or support vector machines or, you know, some kind of random forest business, okay? You just do model.fit x comma y. Okay, so x is your matrix of input predictor x values, and y is your vector one-dimensional array of values. So notice this, you can print out the model coefficients, model.coefficient underscore, okay, and it will print out our estimate of kind of the slope here. All right, and it says the slope estimate is 0.827. We can get the intercept. The true value is 1, and it estimates it based on our data to be 1.0014. So scikit-learn has a different philosophy about fitting models, right? So if you think back to your 101A class, was that last year? I don't know when you guys took 101A, okay? Last winter. So when you took 101A, I imagine your professor stressed the importance of like checking the model assumptions, right? So what are the assumptions that we make when we do ordinary least squares regression, multiple regression, whatever it is, right? What do you do? Huh? Constant variance, right? That's like the one that's like constantly violated, and we say, well, it was violated, but maybe it's still okay, right? What else, how else do you know if your model is valid or not? Yeah, you have to look at your residuals, you check normality, you know, you run all of these, you know, whatever we did in stats models, you get like, you have p-values for each of your coefficients. You have all of these things. You're supposed to check for leverage and all of these things, right? Scikit-learn does not take that approach, okay? Like, so linear regression is very well understood. It's been well studied. We have all of these diagnostic things, right? So you call R and you do plot on the LM model and it gives you 4 plots and you're supposed to look through them and you go, okay, this is a good sign or this is a bad sign. Like this is clearly like my assumptions have been violated, right? So there's lots of assumptions that we make for linear regression. It's well understood. We know what it looks like to violate these assumptions, okay? The same cannot be said about a whole bunch of these other machine learning models, right? Like for a neural network, what assumptions are we making? What are my residuals supposed to look like? I don't know, okay? Support vector machines, what assumptions are we making there? What are my residuals supposed to look like? How do I know if I've made any model violations, okay? It's a lot more complex, and the answers haven't been fully understood. All we know is that, hey, it makes good predictions, so it can't be totally bad, right? That's kind of the philosophy that a lot of machine learning does. For better or worse, I don't know. This is kind of like where we are. And so scikit-learn just says, you know what? If you want diagnostic plots, this is not the package for you, right? Go to stats models. Stats models will give you the diagnostic plots. You can check for leverage. You can check for all of those things. Your residual plots, check for normality, okay? So even the fact that you're getting the intercept and the coefficient is not something that scikit-learn like encourages, okay? That's why they put an underscore. The underscore here is kind of a signal to us that like it's available if you ask for it, but it's not kind of a main thing that we're trying to push, okay? So Seaborn won't even give you the intercept and the coefficient. Like they say, no, that's not what we do, okay? Scikit-learn will give you the intercept and coefficient if you ask for it directly, okay? But they put an underscore next to it almost as a signal like this is not really what we want to do, okay? So it pretty much bases all of scikit-learn says, how do you evaluate if a model is good or bad? It runs off of cross-validation, and I don't think I'm going to talk about that just now, but it uses all of that. Okay. So anyway, let me just show you just some other stuff. So you define your model, okay, and then once you define your model, you do model.fit, okay, and you can ask for the results of that. You can take in new values, okay, and so here I'm going to make this a matrix, doing the 21 values from 0 to 10, basically step size 0.5, okay, and then you can say model.predict. So these are probably like, as far as scikit-learn goes, the 3 steps are define your model, model.fit, model.predict, and pretty much all the models run in that system. Model.fit. You have your y vector of values, okay, your one-dimensional array. You have your x matrix of predictors. Model.fit, x, y. Model.predict, your new x's without the y's, okay? And so when we do this, it spits out, this is what we predict, okay? So here, I'm going to do a scatter plot of my original x and y data, and then I'm going to go ahead and put in the predictions that it produces in red, okay? And so what do we see? The blue dots are the original things, and this is my prediction, okay? So I did scatter, so it draws it as this. If I just did, I think plot defaults to just kind of connecting all of these things, right? If I get rid of the marker there, okay? So this is kind of like your fitted line, and we have that, okay? So that's scikit-learn. You can ask for the residuals. You can like kind of calculate these yourselves by doing y minus the prediction, okay? Print out the residuals, ask for the mean of the residuals. We're gonna get 0, right? 10 to the negative 16. Make a histogram of the residuals. But this is like this is a lot more manual, right? And plot out the residuals ourselves. Like we can do this, but this was a lot more manual work, okay? It's scikit-learn. You can click the linear regression example, and it shows you all of this stuff, okay? But you don't have a whole lot of stuff regarding diagnostics, okay? You have a few things like give me the mean squared error and the variance score and stuff, okay? Your R squared value, okay? And so these are things as far as metrics go, as far as, you know, comparing different models. So you have these. But as far as diagnostics, scikit-learn takes a very different approach to diagnostics than what we might be accustomed to, okay? We're accustomed from the statistical approach, and scikit-learn very much takes a machine learning approach where we evaluate how good or bad a model is based on its ability to make predictions, okay? All right, here's the Boston housing data set. are you guys familiar? Like this is, it's like very old data where they looked at like the median value of homes from like the 1970s or something, and they include like some questionable variables about demographics and stuff in there. So anyway, you can ask for this. There's something called, the data is loaded as what we call a bunch, okay? It's like a dictionary, okay, except it's like a list, kind of. So the bunch contains things like the data, the feature names, the description, and the file name. So you can ask for like boston.data.shape. You have 506 rows, 13 columns. You can ask for the target. So it's split into the predictors, the data, and then the target is what we're trying to predict. These are the 506 values, okay? You can ask for the feature names. These are the names of the columns in your data. You can ask for the description, and it lists off all of these things, right? And again, this was collected, this data, I don't think, was gathered in the 1978, and so it contains all sorts of stuff, and the prices, you're like, how are these prices for homes, right? These are like my car costs more than this, right? So the data is stored somewhere on your computer. You can actually load up the CSV file itself, okay? And it's, the data is stored as a NumPy array, okay? But the important thing is that it's formatted the way we like it. The predictors, your X variables, are in a matrix form, and then the values that you're trying to predict is a one-dimensional array, right? And so as far as that goes, it's very easy. You just go model fit, model predict, and stuff like that, okay? So if we wanted to fit the entire data set, okay, well, here I'm going to like turn it into a data frame, but you don't have to do this, okay? This is just kind of what it looks like. And then if we wanted to make it something that like we can analyze, you can take the column names and take the feature names and do that, and you have all sorts of stuff here, okay? Some kind of values, and again, I don't even remember what these things are. Percent lower status of the population. I don't know what that means, okay? But here it is, right? And then we can just kind of look at the values that we're supposed to predict. And I think this means the median price of the home was $24,000 or something. Something like that, right? So I can't even imagine. That's like 1 year of rent. Okay. What? Right? The median price of a home was $24,000 in Boston, 1978. So good luck finding that today. All right. So if we wanted to, like, we could add this to the data frame and look at this, okay? But we don't have to do this, okay? As far as scikit-learn goes, all we have to do is we're going to define the linear regression model, okay? And just for what we'll do is I'm just going to take these columns, crim through lstat, okay? So we're going to use that as our X matrix, okay? But I could have just plugged it in like this, okay? The only reason why I'm doing this is so that we can get column names, okay? But if you don't care about the column names and you just have predictors and you're fine with them being numbered 0 through 12, you don't even have to do this, okay? But here I'm going to define my X as this data frame where I'm going from crim to lstat. So we're going to take that as our predictors. We have our model defined, okay? This is a series, and we can just do fit X based on, or fit the target using X. You can ask for the coefficients and it will spit these out. You can ask for the predictions and it also spit those out. But we can kind of plot this. This is what we predicted. These are the actual values. and we see what's going on here. Something weird is going on, right? We should investigate all of these things where the actual value is 50. Maybe this seems like there's an artificial limit in our data. Something is not quite right as far as something's going on here, okay? But unfortunately, we don't have a whole lot of data. So this same thing that shows up here is something, and you can just, the score, this is kind of your R-squared value. And this is like, how good did you predict? I see some nonlinearity as far as the residuals go. There's probably some kind of thing here. We also have this is an indicator. You got a diagonal line in your thing. It probably indicates an artificial lower limit or artificial upper limit in your data set. So if you were trying to predict like baseball player salaries, you're going to see this hard limit, this strange diagonal line in your residuals because there's a starting salary, like $500,000 for starting salary, and so that produces some artificial, like this weird lower limit, because we know that rookies who start in baseball, some of them are worth more than others, right? But they all get paid kind of the starting salary of, I think, $500,000. I don't know what the starting salary is for the major leagues, but something around that. What's that? No. Is $500,000 a lot or a little? Sounds like a lot, but how much does Mike Trout make?
About 35 mil.
35 million a year? Yeah, and he's got like a 5-year contract or something?
He just signed a 12-year contract.
A 12-year 12 years? That's a long time. It's a long time. He's going to be like a bajillion years old by the end. I mean, 12 years older. Okay, but but yeah, so that's a lot, right? And then you got rookies that probably worth more than $500,000, but as far as making money for the business. All right, well, anyway, that's this. This is just kind of a very, very brief intro that I think will be useful for your projects. You don't need to study this for your midterm. So do those data camp projects. Make sure you work through the practice midterm from last year. If you want a place to work on Friday, like you don't, like your place is, I think we can work here. I should double check, but I'll see if I can reserve a place here. But I think we can work here on Friday, and it should be okay. So I'll send out an email to confirm or deny that. So we'll do that. Okay, thanks everybody.